General relativity models gravity as the curvature of spacetime, but when dealing with extreme mass, like the core of a black hole, the mathematics predict a singularity, a point where spacetime curves infinitely deeper, and the predictive equations simply break down. This mathematical breakdown happens because of a single, unstated assumption built into standard models: the belief that the spacetime manifold is infinitely compressible, capable of yielding to gravitational pressure forever without pushing back. The elastic torsion framework proposes a strict physical alternative. Spacetime is not an infinitely yielding void. It behaves as an elastic geometric medium. As detailed in the framework's core axioms, this medium has a strict mathematical breaking point. We call this the finite strain limit, denoted as epsilon max. Reaching this exact strain limit forces a change in local mechanics. Instead of allowing matter to compress indefinitely into a zero-dimensional point, the manifold imposes a strict geometric cap. When spacetime is stretched to this extreme boundary, the geometry generates an inward, repelling elastic force, a structural pushback against extreme gravity. Any particle traveling along a geodesic path near a hyperdense mass won't fall inward forever. Its trajectory is modified by this sudden elastic resistance. By tracking exactly what happens when spatial strain is mathematically capped, we can observe how the blocked kinetic energy seeks a new physical outlet, necessitating the creation of rotation, global torsion, and macroscopic cosmological anisotropy. This creates a unique macroscopic architecture, shifting standard spatial models into a toroidal spherical geometry. Replacing infinite curvature with a finite elastic saturation provides a rigorous geometric mechanism that finally unites extreme gravity with a global torsion field. To see how this mechanism works, we isolate the elastic strain field, epsilon. It is a direct function of the local metric tensor. Looking at the derivation, the strain field equals epsilon, bounded by a strict finite limit. Epsilon max must be less than infinity. This limit is entirely intrinsic to the geometry. The manifold is self-contained, with no external space to stretch into once it hits this boundary. As immense mass distorts the local metric, geometric strain accumulates. The region rapidly approaches the epsilon max threshold, hitting the absolute limit of spatial deformation. The geometry reacts by generating a counteracting elastic force vector, defined mathematically as the gradient of the spatial strain. To accurately model the physics here, this repelling force vector is formally integrated into the standard equations of motion for any object traversing the space. The standard geodesic equation is updated, subtracting the elastic force term to account for the manifold's physical pushback. As strain approaches its maximum, this elastic term entirely dominates the equation, producing a severe inward curvature that repels any further compression. The dominance of this elastic force physically halts singularity formation. The infalling energy is blocked, forcing trapped momentum to seek a new dimensional outlet. The specific domain where the manifold completely exhausts its capacity to bend is called the boundary of elastic saturation. The framework defines this boundary as the coordinates where local strain perfectly equals epsilon max. It is not a physical wall in space, but a geometric phase transition surface, marking the absolute end of linear spatial compression. This creates a physical paradox. An infalling particle carries linear momentum, but at the saturation zone, forward movement cannot increase. Hitting the boundary, the vector immediately curls outward into a tight spiral. To conserve energy, linear momentum is forcibly converted into rotational momentum. This is the exact origin of torque conversion. Linear momentum directly maps to rotational momentum at the pi boundary, requiring a minimum stable inversion angle of exactly pi. At the scale of a collapsing stellar core, this localized torque conversion aggregates across the entire boundary, resulting in massive rotational saturation. This systemic, completely unavoidable rotation acts as the direct generating source for a massive, continuous, global torsion field. Infinite spatial density is avoided entirely. The geometry takes inescapable forward motion and twists it into perpetual, manifold-spanning rotational torsion. Zooming out from the trajectories of individual particles, we must account for the macroscopic geometry of this entirely saturated manifold. To support continuous momentum conversion, the boundary requires a specific topological structure, a toroidal spherical hybrid, mathematically denoted as S2 cross S1. We can map exactly how local coordinate frames behave as they travel along the severe curvature of this hybrid shape. As a frame crosses the pi boundary, the extreme spatial threshold forces a complete geometric inversion of its local orientation. Standard spacetime would tear under such stress. The framework introduces the dual inversion operator, a symmetry allowing the manifold to fold back on itself without breaking. This dual inversion directly acts on the local tensors. It simultaneously reverses the extrinsic curvature, the torsion, and the rotational orientation of the space. But to maintain structural continuity, specific scalar quantities remain strictly invariant during the flip, specifically the metric signature, scalar curvature, and the squares of both the torsion and curvature tensors. By rigorously preserving the baseline metric while flipping the directional curvature and torsion, the mathematics yield absolute theoretical stability. The elastic manifold survives extreme cosmic forces because this dual inversion symmetry permanently locks the pi boundary geometry into a stable, inverted state. This structural logic scales. A geometric engine this massive leaves measurable, observational consequences on our actual universe. The mathematics of dual inversion yield a specific invariant direction vector. As a direct result, the manifold inherently possesses a global preferred axis. An elastic universe structurally mandated by rotational torsion cannot be perfectly isotropic. It must have an intrinsic spin direction built into its geometry. By taking this theoretically derived axis and overlaying astrophysical data, macroscopic patterns align precisely with the geometry. This preferred axis directly accounts for long-standing observational anomalies, specifically the alignment of cosmic microwave background low L multiples and highly anisotropic supernova blast propagation. This rotational geometry scales up to affect the mechanics of cosmic expansion. Because the torsion vector is a literal physical force acting on the manifold, it contributes its own effective energy density to the cosmos, defined here as ρt. This forces a direct modification of the Friedmann equation, the formula governing the expansion rate of the universe. The torsion density is added to the standard matter density, altering the Hubble expansion rate based on the elastic saturation of the space. This deterministic geometry is fully computational. It can be rigorously tested and modeled using numerical simulation architectures like the SDF Quantum Lattice V6. The elastic torsion framework functions as a rigorous, unified mechanism, demonstrating that the local breaking limits of spacetime directly engineer the macroscopic shape, stability, and expansion of the cosmos.